Hello, welcome to my talk on panel method for potential flow structure interactions. This is part 2 on boundary integral equation, and this talk is especially for 3D flows. This is a very unique situation for a fluid dynamic problem, since such a boundary integral equation can be easily found in 3D cases, while in the 2D cases, it would be very different. In fact, it is more complicated. This is a rare case in fluid dynamics. The 2D boundary integral equation is more complicated than the 3D boundary integral equations. And this is why I talk about the 3D boundary integral equation first, and I will talk about the boundary integral equation in 2D in part 3. In this talk, I will first introduce the boundary integral equations in 2D and 3D cases, and these are general boundary integral equations. And then we will look at the potential function decomposition for uniform flow and the flow disturbance by the structures. Then we will look at the mathematical transformation for the integrations on the control surface to the body surface. Then we can talk about the final boundary integral equation and the relevant numeric solution. And at last, we will talk about how we can achieve the potential functions in fluid once we already solve the boundary integral equation. As I have shown in my previous talk, the desingularization of the Green's theorem into D, the source function would be given as phi0 equaling to LNR, and the general boundary integral equation for 2D would be given as this. Here, the integration is on the boundary C plus CB, and in 3D, phi0 equaling to 1 over R, and the desingularization in the fluid would give the equation as this. And here, both the potential functions are in fluid. And we also talk about the desingularization on boundaries. In 2D, the boundary integral equation would be given as this, but the integration on the boundary would have a gap, see here. In a similar way, in 3D, the desingularization on the boundary of the fluid would give the boundary integral equation as this. And the potential functions here and here are both on the fluid boundary, either on the structure boundary SB or CB, or on the control surface SC, or on the control boundary C. Now we have a look at the structure fully submerged in the uniform flow, such as the wind in the uniform flow. The structure with the surface SB, see here. And we can make a very large sphere surface SC as the control surface. Then the fluid domain V would be enclosed by SC plus SB. Here, the potential function phi would be decomposed as phi0 plus phi star. Here, phi0 is a known potential function for the uniform flow. So we can take phi0 equaling to u0x if u0 is in the x direction. And phi star is the disturbance potential due to the existence of the structure. So it would generate a disturbance potential phi star. Since generally we know the structure can be represented by the distributions of sources on its surface SB, thus the disturbance potential would be expressed roughly as 1 over r, especially if the distance is far away from the structure surface SB. And correspondingly, the velocity would be proportional to 1 over r squared. And on the large control surface SC, at the infinite, the disturbance potential function would vanish. Thus, at the infinite, the uniform flow can be taken as this. See this control surface, the velocity u0, while the disturbance from the structure would vanish because it would be proportional to the inverse of r squared. As we already shown, the desynchronization on the body surface can be easily obtained, but here the desynchronization is only considered on the structure surface SB, like the plot here, and the boundary integral equation would be given as this. Here, the potential function on the left-hand side is supposed on the boundary SB, while the integral on the right-hand side is on the control surface SC and on the structure surface SB. Now we can write the integral on the surfaces as the integral on surface SB here and the integral on surface SC here. Again here, the potential function phi is on the boundary SB. In this surface integral, there will be a gap on SB, C here, there's a gap here. While on SC, there is no gap, and it can be considered as a complete surface. Next, we need to convert the surface integral on SC to a value on SB. But how we can do that? We will see this in the following slide. In fact, we will see some mathematical beauties in the transform of the integral on SC to the value on SB. Here, we look at the integral on SC, the term given as this. And now we apply the potential decomposition, phi equaling to phi 0 plus phi star. Then the integral on SC can be written in two terms. The term of the integral on SC for phi star and the term on SC for phi 0. Next, we will see what are these terms, this and this. As we have mentioned, since the disturbance potential phi star is roughly proportional to 1 over r because of the distributions of the sources on SB. Thus, on SC, the normal gradient of the potential function phi star would be roughly given as this. It is proportional to the inverse of r squared. And in a similar way, the normal gradient of 1 over r would be roughly proportional to 1 over r squared. Hence, the first term on the right-hand side would be 0, since if we look at the integral and we take the limit when r is close to infinity, and we can see the integrand in this surface integration would be roughly proportional to 1 over r cubic, while SC would be proportional to r squared. Hence, this expression would be roughly given as the limit of 1 over r when r is close to infinity. It would be 0. That means the first term on the right-hand side, the integral on SC would be 0. Now we move to the second term on the right-hand side, the integral on SC, this term. This term can be understood as the integral on SC, and the fluid domain is only enclosed by the surface SC. There is no structure inside in the fluid domain because we have no disturbance potential function here. For such a case, the desingularization in the fluid will give a potential function on SB. In here, we can imagine SB in the fluid. So, the desingularization in the fluid enclosed by SC would give the equation as this. And here, we can take phi 0, the potential function on SB. This equation transforms the integral on SC to the value on SB, given as this. So in here, we look at the desingularization on the control surface SC. If the control surface is very large, and we can desingularize the singularities on the boundary on SC here, and then we will have the boundary integral equation given as this. Here, phi 0 is the potential function on SC. And this equation means the uniform flow and the corresponding potential function phi 0 can be obtained by solving this boundary integral equation. And it also means the uniform flow can be built by distributing the source on the very large control surface SC. Although we don't need to do that because phi 0 is always assumed as a non-potential function. As we have shown before, if u0 is in x direction and the phi 0 would be equaling to u0x. Now we examine the boundary integral equation. As we have shown before, the general boundary integral equation would be given as this by desingularization on the boundary. Here we only interested the desingularization phi on the left-hand side on the structure boundary, not on SC. But it is correct if phi the potential function on SC. Our purpose is to get every term on SB. As we have shown in the previous slides, after the mathematical derivations, we have the boundary integral equation from the general boundary integral equation. Here we can see the boundary integral would include boundary integral on SC and on SB. But here we have used the mathematical derivation to transform the boundary integral on SC to the value on SB. So we can see the integral on SB only here, and the potential function phi here on the left-hand side is the potential function on SB, as we have mentioned in the previous slide. And also the potential function here is on SB as well, which is actually the value transformed from the surface integral on SC. Now the equation is only on SB only. Here we look at the problem. The uniform flow passes through a structure. The uniform flow velocity u0. and the corresponding potential function phi 0. Due to the existence of the structure, the potential function can be expressed as phi equaling to phi 0, the potential for the uniform flow, and phi star, this is the potential function due to the disturbance of the structure to the uniform flow. Thanks to the superposition principle for potential functions. In here, we apply the long penetration condition on the structure boundary given as this. The normal gradient of the potential function phi with regard to n, so it is 0 since the structure is fixed. The normal velocity on the structure is 0. Then we apply the boundary integral equation. This term would vanish. Therefore, the boundary integral equation would be given as in this form or in this form. And now everything is on the structure boundary on SB. This is the boundary integral equation for solving the potential function for the structure fully submerged in the fluid in 3D. Flows of a structure fully submerged in the uniform flow. Now in this slide, we will see how we can use numerical scheme for solve the boundary integral equation. For applications, the structure surface SB would be discretized into many small panels, see these panels. And on each panel, the fluid potential function can be regarded as a constant value. For instance, on the J's panel with the surface delta Sj, this is the source panel with the center coordinate xj, yj, and zj, and the K's panel with the surface delta sk. This is the field panel. Its center coordinate is xk, yk, and zk. And if we discretize the boundary integral equation for this, we have the expression as this. Here, the summation of the integral on the surface, but j would not equal to k. And in this integral, we can also see on the integral delta Sj, we move out phi j because on Sj, the small panel, the potential function phi can be taken as a constant. Thus, it can be moved out from the integral. Then the integral would be only on this expression. Here, Rjk would be calculated as the distance from the source panel to the field panel, given as this. And phi 0k is a non-potential function. If u0 is in the x direction, it will be calculated as this. And in a more general expression, the non-uniform flow, its potential would be given as this, and u0, v0, and w0 are the velocity component of the uniform flow in x, y, and z direction. And if we write the equation in a simultaneous form, it would be given as this. Here, the coefficient a, jk, when j equaling to k, ajk would be equaling to 2 pi. Otherwise, ajk would be calculated as this expression. And solving this equation, we can obtain the potential function phi on each panel phi1 to phi-n. And we can see here the uniform flow potential function performs as the activation for the potential flow phi1, phi2 to phi-n. In here, we will have a look how we can calculate the potential function in the fluid once the potential on the boundary SB is calculated. As we have shown before, using the desynchronization in the fluid enclosed by SC plus SB, it is given as this. And here, the potential function on the left-hand side would be in the fluid, see here. And in a similar way, we need to transform the integral on SC. Here we can write this surface integral into two terms on SB and on SC. And in a similar way as we shown before, for the potential function on SC, it would be equaling to minus 4 pi phi 0. And apply the no penetration condition, this term would vanish. Thus, we have the expression for calculating the potential function in the fluid phi, given as this, or calculated as this. Here, phi 0 is known, and phi here is solved using the Penner method. Thus, we can calculate the potential in the fluid phi. These two potentials in fluid, and this potential on SB.